Hello and namaste everyone. Welcome to lecture 23 of this NPTEL course on stochastic approximation. So in the previous week we started combining all the tools that we have studied in order to understand the asymptotic behavior of stochastic approximation algorithms, right. In this week we will continue that discussion and try to finish the proof of the main theorem that we started, right. So let us do a quick recap of what we were trying to do, right. We were trying to prove this theorem, right, and recall that this theorem said consider the stochastic approximation algorithm given by this update rule xn plus 1 equals xn plus alpha n times h of xn plus mn plus 1. Further, suppose the 4 assumptions a1 to a4 hold, then the sequence xn generated by this update rule converges to a non-empty, compact, connected and an internally chain transitive invariant set of the limiting ODE x dot of t equals h of x of t. So again I would like to highlight that the stochastic approximation algorithm by its nature is stochastic, whereas this limiting ODE is deterministic. Now in the previous week I made a mistake and said that the limiting set is actually path connected. I would like to fix that, okay. I later on realized that one can actually only show that this limiting set is connected. So now I am going to define this notion of connectedness and then tell you how one can show that this limiting set is actually connected, right. So a subset of RD, let us denote it by A, is said to be connected if it cannot be, notice that it is cannot and not can. So a subset A of RD is connected if it cannot be written as a union of two non-empty disjoint open subsets of A, where this this notion of openness is in the concept of subspace topology. So let me elaborate. A subset of RDA is said to be connected if there does not exist sets U and V, okay. So I think I made a mistake here, this should not be this, okay, U and V such that now you require that these sets be disjoint, right. So there should be two, you should not be able to write A in this fashion, which fashion, that you have these two non-empty sets U and V such that U intersection V is empty and A equals U union V, right. And when I say that A, U and V should be open, right, in the subspace topology, I require that U be Q intersection A and V be R intersection A for so I think I have made a bunch of mistakes here, sorry about that. So this should be Q and R being open in RD. Is this okay? So let me say it again. So A is connected if there does not exist two non-empty sets U and V such that their intersection is empty and A can be expressed as U union V, where U and V are open in the subspace topology, meaning U can be expressed as Q intersection A and V can be expressed as R intersection A, where Q and R are open sets in RD. So maybe some of you may be a bit confused about what I am saying. So let me elaborate. So let us say you have a set of this form, okay. So let us say something like this, right. So let us say this is 0, this is 1 and maybe this is 2 and let us say this is 3, okay. So your set A is 0 comma 1 union 0 comma 1 union 2 comma 3, right. So the point is that a set which can be written as a union of disjoint sets, okay. So ideally one would expect that such a set is not connected, right, and this is what this result says. Now notice that 0 comma 1, this interval is actually an open interval. However, the interval 2 comma 3, because it is closed from one end, this set by itself is not open, okay, this set by itself is not open. However, this set can be written as, let us say 3 by 2 comma 3 intersection with A, right. So, if you take A intersection 3 by 2 comma 3, I hope you agree that you will indeed end up with 2 comma 3, and from or by this logic one can see that you can express 2 comma 3 as A intersection some open interval, and hence this 2 comma 3 is open in the subspace topology relative to A, right. So, because of this reason we can say that this union of set can be expressed as this set union this set, both of which are non-empty, they have nothing in common and they are open in the subspace topology. Hence, the union of these two intervals is indeed disjoint, and hence it is not connected. Is this okay? And so, whenever you are not able to express A in this fashion, we would say that A is connected, and when you are able to express A in this fashion, that is in terms of U and V, we will say that A is not connected. Is this okay? And the formal definition of two sets being open in RD is that so here I have sort of specifying when is a subset Q of RD open. A set Q of RD is open if there is some room to maneuver at every point in Q. Specifically, if you consider any point x in Q, there should exist a R, which is you can think of it as the radius, such that the ball centered at x of radius r is fully contained in Q, where B of xr is the ball of radius r centered at u centered at x, sorry, right. And so I will maybe also give the formal definition of this ball. So, this is B of x comma r equals all y such that the distance between y and x is strictly less than r. Okay, so, this is referred to as the open ball of radius r centered at x, right. So, now I hope you have got some intuition of what do I mean by a set being connected. Now, let us recall what we were trying to do. If you recall, the limiting set that we were thinking about was defined in the following sense, that is A equals the intersection of the closures of the tail of the linearly interpolated trajectory obtained from xn's, right. And the claim is that this set A is actually connected. Okay, so the claim is that this set A is actually connected, and the way we show this is that you first show that the tail of this linearly interpolated trajectory is connected for any t bigger than equal to 0, and the way you have to show that this is connected is by showing that this set can be expressed as the image of the connected set t comma infinity. So, if you think of t comma infinity, this is an interval on the real line, right. So, somewhere you have t and this is this set. So, I hope you agree that this set, the one that I am highlighting over here, cannot be expressed as a union of two non-empty sets such that they are disjoint and both of them are open in the subspace topology. So, this set indeed is connected, and this set over here is the image of this connected set under the continuous function x bar. So, recall that x bar is obtained by linear interpolation and hence it is trivially continuous, and since this is a connected set and this is the image of this connected set under your continuous mapping x bar, one can apply some concepts from real analysis to conclude that this set must be connected, and since this set is connected, we can thereafter conclude that the closure of that set is also connected, and since A is the intersection of nested connected sets, one can conclude that A also is connected. Is this okay? So, last week I made a mistake and said that this set A is path connected. I would like to highlight that path connected is a stronger notion of connected, which means that every path connected set is actually connected, but the converse is not true. That is, you can have sets which are connected but are not path connected, right, and towards that I had given one example last time, right, which I have repeated over here. So if you consider this set S, which is the union of these two subsets, okay. So the first subset consists of pairwise elements, or two dimensional coordinates, where the first element x comes from the interval 0, 1, which is open at 0 and closed at 1, and the second element of this tuple is sine of 1 over x, right. So this part is a subset of R2, right, and you take the union of this subset with this subset of R2, which includes all points of the form 0, y, where the first coordinate is 0 and the second coordinate is some number between -1 to +1, right. So if you consider the union of these two sets, one can show that this set is actually connected, but it is not path connected, okay. So this set is formally known as the topologist's sine curve, and you can read more about it online, and in fact figure out why is this set connected but not path connected, right. So in that sense, if you consider a sequence made up of 1 over n comma sine 1 over n, so each xn is two dimensional coordinate, and if you look at the linear interpolation of this sequence, right, one can show that the closure of this sequence, right, is connected, but it is not path connected. So this is the reason why in general we will not be able to show that such sets are path connected, but we would only be able to show that it is connected. Alright. So this in some sense fixes the issue that unfortunately I had made in the previous week. I hope this is now resolved. Now we go back to proving the main theorem, right, and if you remember, what we had done last week was to establish the main theorem assuming the following technical lemma, right. So we had said that suppose this lemma 1 holds, then the main theorem holds, and now what we are going to do is we are going to prove this lemma 1. In particular, throughout this week we will be proving bits and pieces of this lemma, and put together that will give us the full proof of lemma 1. So what does lemma 1 state? It states that under assumptions A1 to A4, the following two statements hold almost surely. So what are these two statements? For any t bigger than equal to 0, this quantity over here goes to 0, right. So what is this quantity? Well, it is the distance between your linearly interpolated stochastic approximation trajectory and a suitable solution of your limiting ODE, right, and you look at the distance between these two trajectories within the window that starts at S and goes all the way up till S plus t. Thus we are looking at a window of size capital T, and this limit ensures that the starting point of this window goes to infinity, right, and then we have a similar result where instead of looking at the window S to S plus t, we look at the window S minus t to S, right. So we sort of look t time units before S, and here we are looking at capital T time units after S, right. And what is this excess of t? Well, formally excess of t is this quantity over here. So this is the solution of this ODE, which at time S has to pass through x bar of S. Is this okay? And pictorially what this lemma is trying to tell us is that if you think of this red trajectory over here as the linear interpolation of your xn's, okay. So on your x axis you have time, and on the y axis you have Rd in an illustrative sense, right. So these are your different elements generated by your stochastic approximation algorithm. Now you linearly interpolate them, in that way you get this red trajectory. So now you pick some S on the timeline below, right, and look at the window S to S plus t. So what you do is you start the solution of your limiting ODE, which is denoted by blue color over here, from where your linearly interpolated trajectory is at time S, right. So you can see that at time S the blue trajectory and the red trajectory are at the same place, right, and thereafter the blue trajectory is governed by the deterministic limiting ODE, whereas the red trajectory is governed by your stochastic approximation iterates, right. And what this lemma 1 says is that if you look at the supremum distance between these two trajectories within this window, then as s goes to infinity, that is as your initial time instance goes to infinity, this gap between, or the gap between these two trajectories will go to 0. Is this okay? And now we are going to formally prove this lemma, right. So the proof of this statement and the proof of this statement more or less follow similarly. So what we will do is we will only focus on proving the first part, and the second part will be left as an exercise. Is this okay? So how to prove the first part? The first thing you can observe is that from our update rule we have xn plus 1 equals xn plus alpha n times h of xn plus mn plus 1. So if you look at this update rule over, let us say m many time steps, okay. So here you have m. So if you look at this update rule over m many time steps, then one can see that xn plus m equals xn plus the sum of quantities of this form plus sum of quantities of this form, okay. So let me just quickly elaborate why did I get this. For example, you would have x1 equals x0 plus alpha 0 times h of x0 plus m1, right, and similarly you would have x2 equals x1 plus alpha 1 times something, right. So wherever you have x1 you replace this quantity, and one can see that one can express x2 equals x0 plus this quantity plus this quantity. That is exactly what we have over here. Is this okay? So now we are going to take a look at this quantity and this quantity separately and see how does this behavior compare with the solution trajectory of an ODE, which let us say is started from x1. So we are going to do this comparison, right, and in this class what we are going to do is we are going to focus on this part, okay, which is what we had over here, right. So this expression is the cumulative noise in the update rule. Cumulative noise meaning at time step n we add the noise term alpha n mn plus 1. Is this okay? At time step n plus 1 we will add alpha n plus 1 mn plus 2 and so on, right. So at each time step we will be adding certain noise to our update rule. So this one can view as the cumulative noise that is there in our update rule, right. So what we are going to ask is what can we say about this cumulative noise, okay. Now you have to keep in mind that cumulative noise in general will be good for us, for the reason that at any particular time instance the noise is actually going to push you in a certain direction, right. So let us say at time instance n the noise pushes you this way, at time instance n plus 1 the noise pushes you this way, and maybe at n plus 2 it pushes you backwards, and the subsequent thing it pushes you forward, and so on and so forth, right. So at any given time instance the noise is going to push you in some arbitrary direction, but because of its very nature that its conditional expectation is 0, what we would hope is that if you add enough of these noise terms the cumulative effect sort of cancels out, because at some point you are pushed forward, maybe at some other point you are pushed backward, and so on and so forth, so that the cumulative effect is negligible, okay. So that is why often we work with cumulative noise expressions, and now we are going to formally see why a term like this, okay, has negligible effect asymptotically, okay. So you will see what do I mean by all these terms as we move along. So what we will do is, as a first step we are going to introduce this notation zeta n, which is the cumulative noise from time instance 0 to discrete time instance n minus 1, right. So one can see that from this definition if you put n equals 0, this is n minus 1, so which is minus 1. So whenever the upper index is smaller than the lower index we will presume that the sum is 0. Accordingly I have said zeta 0 is 0, right. Now if you put n equals 1 over here this expression will be 0, so we only have to look at one term with k equals 0, and hence we will end up with alpha 0 m1, and similarly one can see that zeta 2 is alpha 0 m1 plus alpha 1 m2 and so on. Okay. Recall from our assumption A3, okay, so which was done in the previous week, right. So you can look at that lecture and explicitly see what is A3. So one of the statements that we had presumed under A3 was that this noise sequence is a Martingale difference sequence, which means that almost surely the conditional expectation of Mn plus 1 is 0, where Fn is the sigma field generated by x0 m1 all the way up till Mn. So one can view this as the information that is there available until time n. Is this okay? So what this says is that given all the information that you have until time n, the conditional expectation of this is 0, right. And from this one can see that if you take the conditional expectation of zeta n plus 1, okay, which is the sum of terms of this form, right, you can break this sum into the first n many terms, right, and then you can look at the last term over here, right, and zeta n, right, if you go back to the definition of zeta n, okay, this is made up of terms like alpha 0 m1, alpha 1 m2 all the way up till alpha n minus 1 mn, right. So in other words, zeta n is a sum of quantities, okay, whose value is available at time Fn, right. In some sense or formally one can show that zeta n is measurable with respect to Fn, and since zeta n is measurable with respect to Fn, the conditional expectation of zeta n with respect to Fn is zeta n itself, and then we are left with the conditional expectation of alpha n mn plus 1, right. So we are making this jump by using the linearity of conditional expectations, right, and the fact that your zeta n is measurable with respect to Fn, right. So by using these two facts one can show that the conditional expectation of this is zeta n times this, right, and thereafter by making use of the linearity property of conditional expectation we can write this expression as zeta n plus alpha n times the conditional expectation of mn plus 1 given Fn, right, and by our assumption in A3 we know that this is 0 and hence alpha n times this will be 0 and hence this whole term will basically be zeta n. So what we have managed to show is that the conditional expectation of zeta n plus 1 is zeta n, where all these equalities are presumed to hold almost surely, okay. So from this relation one can conclude that the sequence zeta n, okay, is actually a martingale with respect to the filtration of sigma fields Fn, right. So recall that your Mn sequence was a sequence of martingale differences, whereas your zeta n is actually a martingale, right. Now as soon as you see martingale one can ask, oh, now can we make use of the martingale convergence theorem that we had studied before? So the answer is yes, and we will now see how to make use of this martingale convergence. Is this okay? So the first thing we have to observe is that because it is a martingale, the expectations will remain the same throughout, and in particular one can show that the expectation of zeta n is actually equal to expected value of zeta 0, and recall that zeta 0 is 0 almost surely, and hence the expectation is 0 for all n bigger than equal to 0. So let me just say 0 here, right. So I will end the class over here, but in the next class we will see how we can make use of the fact that zeta n is a martingale sequence along with our assumptions in A3 to show that zeta n converges, and once we establish zeta n converges we will use that fact to show that the tail of the cumulative terms of the noise arising due to this mk plus 1 will have negligible effect in the behavior of your xn's compared to the behavior of the solution trajectories of your limiting ODE. So we will see all these things formally in the next class. Until then, bye and thank you.